SwayamPrabha. Digital India. Educated India.
In the previous lecture, we had derived an evolution equation for the thin film, and this involved the following forces: gravity, viscous forces, and surface tension. The gravitational vector was pointing from the gas to the liquid. In other words, you would expect gravity to be a stabilizing force. Similarly, you would expect surface tension to be a stabilizing force, because any undulations that you create on the thin film leads to an increase in the surface energy, and this would be unfavorable, and therefore you would expect that surface tension would cause the thin film to return to its original flat, undisturbed state. And finally, when any motions are created in the thin film, probably because of undulations that one has created at the interface, these undulations would generate motions in this thin film, and these motions would generate viscous resistance, and therefore viscous resistance would again be a retarding force. So in the discussion that we have achieved so far, there is no mechanism to cause a rupture of the thin film. That is exactly what we are going to rectify in this lecture. We will be introducing a new force which causes rupture. This is a non-hydrodynamic force called the van der Waals force. So what we'll be looking at this lecture is what exactly is this van der Waals force? How do we understand this force? What are the origins of this force? And finally, how does it enter our equations of motion? Now, the discussion on van der Waals force will be done at a very rudimentary level. Students who want to go into more details about this topic can consult more advanced sources. The topic of van der Waals force is particularly difficult for a course like this because it has quantum mechanical origin, and that's clearly beyond the scope of a course like this. So we will dive into this discussion of what is the van der Waals force. So our discussion essentially begins with the equation of state for an ideal gas. So for example, if we take an ideal gas, the equation of state would be our well-known equation, which is PV equals RT. Now, you can also state the ideal gas is a non-interacting gas. So in other words, if you have point particles in an ideal gas, these could be gas molecules or atoms, these point particles do not interact if they are governed by the ideal gas equation. But we know real gases do not behave like this. So if we were to look at a real gas, so this is given by the so-called van der Waals equation of state. The general form of the van der Waals equation of state is given by P plus a new term, which is A by Vm square, it is sufficient for us to know that these additional terms that we have here, especially these quantities constants A and B, denote interaction between the molecules of the gas. Now, to understand what is the source of this interaction, one has to first understand what is the typical source of interaction in molecules and in atoms. Let's consider an example of a covalent bond. Okay, so let's consider a oxygen bond. The oxygen, it's a double covalent bond, and each oxygen has in itself has a deficiency of 2 electrons in its outermost shell, and therefore it needs to collaborate with another oxygen atom to basically get the necessary number of electrons. And it does this by basically forming a bond, sharing 2 of its electrons with another neighboring oxygen atom, and that basically creates a very strong bond. Now, one can ask, what is actually holding this oxygen molecule now? The O2 molecule, what is actually holding it is basically the double covalent bond. The sharing of oxygens, sharing of electrons is basically forming this double covalent bond. It's a very strong bond. Now, this is also true for other kinds of bonds. For example, we can have an ionic bond, and we see this ionic bond in a molecule like NaCl, right? Now, these bonds basically are much stronger than the van der Waals forces. Now, what exactly are these van der Waals forces and what is their origin? Now, let's consider a very simple situation. Let's consider 2 molecules. I'll call them as A and B, right? So molecule A is basically, let's say, a bunch of, is shown like this. This is a very simplistic drawing, of course. Let's say this is molecule A, and we have molecule B here. What exactly is this molecule A and B is not important for this discussion. Okay, it just suffices, it's enough for us to say that these are 2 different kinds of molecules. Now, we will take a gross picture representation of this molecule. Instead of showing them as individual point particles, we will say that this molecule A is basically has some shape like this, and molecule B is this, right? Now, what happens in a molecule A? Now, this molecule A has basically electrons all around it. There's an electron cloud around this molecule, and this electron cloud constantly keeps fluctuating. This is especially true for non-polar systems, where you have this electron cloud. Because it's already fluctuating, at any given instant of time, there is no reason to expect that the electron cloud will be uniformly distributed around the molecule. And there is a small asymmetry that is created for brief instants of time. And the small asymmetry, we will represent this as a polarization. What exactly I mean by this polarization? Let us say there is a increase in the density of electrons on the right side of this molecule. This creates a delta negative on this side, and as a result, it automatically creates a delta positive on the other side. Now you can say that this molecule is now in a polarized state, right? So what I'm representing here is an electron rich region. Okay, and this polarized state, now once you have an instantaneous polarized state, it creates an instantaneous electric field. And if you bring another neutral molecule, let's say molecule B, which is neutral, it does not have any dipole. If you actually bring it to its neighbor, then what will automatically happen is this molecule B will start basically get a brief positive delta there. On the far end of this molecule will be a brief delta negative. So in other words, the very process of actually bringing one polarized state dipole near another molecule would be to create an instantaneous dipole. So you have, on one hand, on the left side, what you have is an instantaneous dipole. And on the molecule B, what we end up doing is to get a induced dipole. Now, because of this dipoles that are created for brief instance of time, we end up getting a net attraction between these dipoles, right? So this force can also be referred to as a fluctuating dipole induced dipole force. So this is a fluctuating dipole induced dipole force. Now these forces basically come under the larger description of London dispersion forces. These are also sometimes referred to as charge fluctuation forces. Now these forces, because they crucially depend on the fluctuations of the electron density, if one wants to build a detailed theory of the exact nature of these forces and the magnitude of these forces, then one needs to look at quantum mechanics, because the the fluctuation of these forces are clearly of quantum mechanical origin. So that is clearly beyond the discussion of a course of a course like this. Now, but let's basically look at the strength of this force. Now, let's understand that there are a few new words that we have automatically introduced here. So, we've introduced this word called polarization. One needs to understand what is the polarizability of a molecule. For example, this is typically represented by quantity alpha. For example, if you take a large molecule which has a large number of electrons, it is much more easy to create a polarization in that molecule. Meaning, if you bring another molecule which has a dipole near this large molecule, then you can actually it's much more easier to generate a dipole, induced dipole in such a molecule, right? So, but if the molecule is much smaller, then it's much harder to create this induced dipole. The strength of this dipole is much weaker because the electron cloud density differences are much smaller. So therefore, this is also directly, if you look at fluorine versus iodine, the boiling point of iodine is much larger than the boiling point of fluorine. This is precisely because of this van der Waals force. But the van der Waals force has many other uses. I'll give you a few examples. The van der Waals force basically tells us about the condensation of gases into liquids. It appears in biological physics, especially in organic matter. It appears in condensed matter physics, especially in liquids and solids. And these dispersion forces basically, this is basically what causes the sublimation heat of hydrocarbons. Things like liquefaction of oxygen and nitrogen into their liquid phases are also dominated by these forces. We would not normally be able to explain this phenomena without understanding interaction of these gas molecules. Now, the because of the work of van der Waals in explaining many of these phenomena, he was awarded the 1910 Nobel Prize in physics. In fact, he is attributed to creating this field of the molecular origin of these intermolecular forces. Now, let's basically understand the strength of this force. Now, to understand the strength of this force, let's start with looking at what is the nature of the interatomic potential. For example, if I say the interatomic potential is given by this quantity W of R, then we would typically have a shape like this, and the far field attraction is given by this W of R will be proportional to 1 by R power 6, and it's an attraction, therefore we have a constant C to the R power 6. This constant C is referred to as the London constant or the van der Waals constant. Okay. So once we basically have, if we understand what is the nature of interaction between two atoms, we can basically extend it to macroscopic bodies. This is exactly what London did. Okay, Fritz London, a German physicist. So Fritz London basically attempted the problem of looking at interaction between two macroscopic bodies. In this case, let's consider the geometry that Fritz London considered. So we have two spheres, and let's say the center to center, the line joining the centers is shown here, and the radius of one sphere is R1 and the radius of another sphere is R2, right? And we will parameterize this problem in terms of the separation distance capital D, right? So how would we basically go about determining the interaction potential? So what we would do is we would take a small part of on sphere 1 and basically consider its interaction because of every molecule in this little strip. So in other words, we are looking at interaction forces from every molecule, from every part of the strip. We would have to integrate across this, and similarly we will have to do across the entire body, and this is only at one particular location. And when we do this over the entire surfaces of bodies, then what we get is we can expect that the energy of interaction between macroscopic bodies or for macroscopic bodies okay, like of the type that I have taken here, this energy of interaction, you would expect it to be a function of the size of the bodies, R1 and R2, size of the two spheres, along with a bunch of other parameters. This bunch of other parameters would be the geometric parameter, which is the separation distance, and a new parameter which is referred to as, which is commonly written with the alphabet A. This new parameter is called the Hamaker constant. So for example, for interaction in vacuum, between two atoms, this parameter A essentially becomes pi square C rho 1 rho 2. What are rho 1 rho 2? C we've already seen. This is the van der Waals constant. And rho 1 and rho 2, they are the number densities. That is, number of atoms per unit volume. For example, if I were to consider the case of water, then it turns out that C, this constant C, turns out to be about 1.4 into 10 power minus 77 joule meter per 6. Remember, we had W of R to be minus C by R power 6. So the units of C would be W of R, which is the interaction, energy, interaction energy, multiplied by the radius power, the distance power 6. Therefore, we have joule meter power 6. And rho in this case will be, because if we look at interaction between two water molecules, then it will be 3.3 into 10 power 28 per meter cube. Okay. And therefore, the Hamaker constant A turns out to be pi square C rho 1 rho 2. Okay. And this comes out to be about 1.5 into 10 power minus 19 joules. So what I'm trying to drive home is that once you know the nature of the materials, that are the nature of the materials, meaning the types of atoms that are interacting, you can calculate this Hamaker constant in terms of the properties of the material, like the number density and the interaction strength, which is given by this van der Waals constant C. Right? We have to remember this unit of C. This is a very important parameter that is relevant for the future discussion on this topic of rupture of thin films. So the unit of Hamaker constant that is the unit of this is joules, and typical value for most condensed matter, solids and liquids, this is typically, it varies from 0.4 to 4 into 10 power minus 19 joules. Okay. Now let us basically return to the case of interaction between two spheres that London carried out. If you look at interaction between two spheres, then we find that two spheres, two macroscopic spheres, of radii R1 and R2. The energy in this case will be minus A by 6D times R1 R2 by R1 plus R2, and we are assuming that R1 and R2 are much larger than D. In other words, we are saying that the separation distance, this D, separation distance D, is much smaller than the size of these macroscopic bodies. Okay, and the reason for this is because this force is only felt when the separation distances are in a few nanometers. Okay, and the force can be now calculated as minus dW by d of capital D, where remember capital D is the separation distance, and this comes out to be minus A by 6 D square times R1 R2 by R1 plus R2. This is basically our force. Now we can basically extend the same calculation to macroscopic bodies of other shapes. For example, for two planar surfaces, let's say we are infinitely planar surfaces. Let's say there is surface A, the material A, and a macroscopic body B. Then we can extend the same calculation again, which is to say that if they are parametrized by a separation distance, let's say h, then notice that the area is infinite for them. So you can't, the volume therefore also would be infinity. So instead of talking about a force per se, we should be talking about force per unit area. And we know force per unit area is a pressure. In this case, it will be an adhesion pressure. And this pressure, because it's a pressure, we'll call it as P. or maybe we'll call it as pi, and this addition pressure will be minus A by 6 pi h cube. Okay. Notice that this is a pressure, so the units is basically force per unit area. Okay. And if this is in this case, this is an interaction in vacuum, meaning A is interacting with B through a vacuum. So there are a couple of points to remember here. So there is a surface of A, which means that on one side you have material A, on the other side you have vacuum. Similarly, there is a surface of B with vacuum, meaning on one side you have B, material B, and you have vacuum. So A and B are interacting through this vacuum. So the properties of the vacuum basically would enter into this Hamaker constant A. Now instead you could also have a situation where you have material A interacting with a material B mediated by another medium we'll call it as C. In this case, the formula will remain exactly the same. P is again exactly minus A by 6 pi h cube. But now this A, the Hamaker constant A will include properties of medium C as well. Okay. The notation was a little unavoidable. Instead of calling it A, B, C, I could have called it 1, 2, 3. But this A, medium A, is different from the Hamaker constant A. Okay. So now when I say it's the properties of medium C will enter, now notice that these interactions between A and B will happen through electromagnetic waves. And this is, remember, these are because of instantaneous dipoles, fluctuating dipoles that are created in A and B. And these fluctuating dipoles, basically the frequency of this fluctuation would automatically affect how the interaction happens through the properties of medium C will affect how these interactions happen. So properties of medium C, such as the refractive index, if C is charged, then the charge density, all of that will enter in determining the Hamaker constant for such a case. So physicists have basically calculated the Hamaker constant for a wide range of combinations. And we will basically not be calculating this from first principles, but we'll be assuming standard values for various situations based on the values available in literature. Now we still have to address one question, which is this a body force or a surface force? Now if you look at Coulombic interactions, those kinds of versus van der Waals interactions, now you could ask, one way to address this question, is it a body force or surface force? The interaction happens because of the presence of surfaces, meaning A and B, in the first case, A and B are interacting with each other because there's a vacuum. If we basically bring two forces, two plates of A and B, two surfaces or two plates, very close to each other, even in vacuum they would attract. This is also sometimes referred to as the Casimir force. Now if you were to change the materials on either side of these interfaces, like by interfaces I mean there is an interface here and an interface here. If we were to change the materials on either side of this interface, does the force change? The answer is yes. So therefore this is strictly speaking a body force. Okay, so Waals forces are body forces. But at the same time, these forces appear when we have interfaces, and therefore this allows us to basically make a simplification. So what do I mean by the simplification? There are two approaches to incorporate van der Waals force into our equations. So one is the body force approach. By body force approach, what we mean is we have the Navier-Stokes equations. By body force approach, we have the Navier-Stokes equations. We will now add a new body force. This is basically my additional force that we have introduced here as a body force term. But we can also do one more thing, which is to incorporate it as a surface force. When we incorporate it as a surface force, we will add a new pressure. The disjoining pressure. Will be added as a surface force. For example, in our discussion so far, we basically had the equations of motion, which were the thin film evolution equation. The thin film evolution equation was del H by del T was given by the thin film evolution equation was given by del H by del T is equal to del by del X of H cube by 3 del P0 by del X. Remember, the problem that we were looking at was a flat substrate over which there is a thin film given by the equation y equals h of x comma t. Now what we can do is, for this thin film, the pressure that we had here was basically the leading order pressure. We had P infinity. This is the atmospheric pressure in the gas. Then we had the gravity term, which is epsilon cube L square rho g by mu u naught times y minus h. This is gravity term, or this is better to call this as hydrostatic contribution. Then we had a curvature term. This is the capillarity term, or the Laplace pressure jump. And finally, we will now have a new term, which is basically the disjoining pressure. This disjoining pressure we'll simply call it as let's call it as pi star of h. Meaning, this is a pressure that directly depends on the local thickness of the interface. And this pi star of h for us, remember the pi of h, this is in a non-dimensional form. Non-dimensional. disjoining pressure. The dimensional form is would be something like pi of h would be a by 6 by h cube. This is the where h is a function of x and t. So if I non-dimensionalize this, let's call this as pi star. This would be pi by, this is a pressure. Therefore, I can directly non-dimensionalize it by the characteristic scale for pressure that we had already done, which was pi divided by the characteristic scale for pressure, if you remember, was mu u naught by L times 1 by epsilon square. Right? And this essentially becomes A by 6 pi times epsilon square L by mu u naught times 1 by h cube. But this h now is a dimensional h, and therefore I'll use the tilde symbol that I had, right? But we also know that the non-dimensional h would be the dimensional h by h naught. This is non-dimensional. Right? And therefore I have the non-dimensional value expression for the disjoining pressure would be A by 6 pi mu u naught. We have epsilon square L by epsilon cube L cube times 1 by h cube. Okay, and this essentially becomes A by 6 by mu u naught times epsilon L square times 1 by h cube. This pressure directly can go into our equations. This is a more convenient way for our analysis because we've derived a simple expression for the pressure, and all I need to now do is incorporate this van der Waals disjoining pressure into my equations, and this will basically contribute to the rupture. But we will exactly see the exact mechanism of rupture and what kind of flow is generated during the rupture process in another lecture. All right. It's important to understand that these forces, the London dispersion forces, have a quantum mechanical origin. Therefore, it would not be possible to elaborate more than what I have done in this lecture. So, what we will see in the next lecture is to start with the evolution equation of the thin film with this van der Waals disjoining pressure, and we will basically do a linear stability analysis of this thin film, and we will see the role of this extra term that we have taken, primarily the van der Waals term, the Hamaker constant and so on, in the stability analysis of this thin film. Thank you.